This lecture is brought to you by CNCB Academy of Science and Technology. Visit us at cncbacademy.com.
Today we are going to start Electromagnetism for Ph.D. entrance exams, and this is the part 1 of the lecture. I am Yassi Sanyal from the Department of Physics. So let's begin. So what's the first problem? So this is the first problem. A beam of light is propagating through a block of glass with refractive index N. The block is moving with a constant velocity v in the direction opposite to that of the beam. Show that the speed of the light beam in the block is c minus nb, n minus v by c. This is the velocity with respect to the lap frame. That is what we are going to have to find out. Now, refractive index is given by velocity of light in vacuum divided by the velocity of the electromagnetic wave with respect to the medium. Medium is designated by M here, and E stands for electromagnetic wave. So, VEM is the velocity of the electromagnetic wave with respect to the medium, and the medium is moving with respect to the lap frame. And we also know the velocity of the medium with respect to the lap. S stands for lap, and that is minus v. So this medium is moving in the minus x direction, and the light is propagating in the plus x direction. So what we have to find out is VEL, the velocity of the electromagnetic wave with respect to the lap frame. So this is simple. So we have to use Einstein's velocity addition formula to find velocity of the electromagnetic wave with respect to the lap frame. And that's it. So in order to find VEL, we have to know first VEM. VEM can be found out through this expression, and then we have to find out velocity VML. VML is also given. So it's just a standard calculation to find VEL. Go to the next problem. A linearly polarized light is passed through two polarizers. The first one at 45 degrees to the original axis of polarization, and the second at 90 degrees to the original axis of polarization. Convince yourself that 1/4 of the original light intensity passes through the polarizer. This is simple. So if initially you have a polarized light, say intensity is I naught. So the first polarizer is placed at an angle of 45 degrees with respect to the initial polarization direction. So what will be the intensity through the first polarizer? That will be I0 cos square pi by 2. So this is the intensity that will be transmitted through the first polarizer. And again the second polarizer is at an angle of 45 degrees with respect to the first polarizer. So this is my intensity at the first polarizer, and so this times cos square pi by 4 will be the final intensity, the intensity that we get at the second polarizer. This kind of stuff. Now we'll consider a problem. Two identical magnetic dipoles of length L, which are free to rotate, are kept fixed at a distance d much greater than L. So in the minimum energy configuration, they will orient themselves in. So there are two options. One will be correct, anti-parallel to each other and perpendicular to the line joining them, and parallel to each other and aligned to the line joining them. So let us go to the picture first. So this is my dipole. So this is the direction perpendicular to the orientation of the dipole. and this is the direction that is aligned with the dipole. Now, if we place a dipole here and a dipole here, this dipole will orient itself in the direction of the field that it experiences here due to this dipole. And if I place a dipole here, it will align itself in a direction which is in the direction of the field due to this dipole. So what I have to find out? First, let us see if the dipole direction is this. What is the field here and what is the field here? Okay. And this is the ordinary direction theta. Arbitrary, this is the general direction theta. So this direction corresponds to theta is equal to 0, and this direction corresponds to theta is equal to pi by 2. So the magnetic field due to a dipole is given by this. So this is the theta that I was talking about in the last slide, this theta. So we are interested in the cases theta is equal to 0 and theta is equal to pi by 2. When theta is equal to 0, that means this term will not be there, and only cos 0 is 1, only this term will be there. So you can see for theta is equal to 0, B will be aligned in the direction of r path. That is, they are written in a field, the direction of the field is in this direction due to this dipole. And when you are considering theta is equal to pi by 2, that is, when this is 0 and then this is 1, so B will be in the direction of theta cap. And what is the direction of theta cap? So theta is increasing here in the clockwise sense, the way I have drawn it. So theta cap will be downwards. So at theta is equal to pi by 2, theta cap, the unit vector in the direction of theta will be downwards. So the direction of the field will be this. So if I place a dipole here, then it will get aligned in the direction of this field. So it will flip. And if I place a dipole here, it will be aligned in the same way as this dipole, because the field is in this direction. Now the question is, which gives us the minimum energy? Remember, the dipoles are free to rotate. So find out the field in each case. When d theta is equal to 0 and d theta is equal to pi by 2, that we have found out. Now evaluate m dot d theta is equal to 0. So what is the, so if the dipole is oriented in the direction of theta is equal to 0, when the field is d theta is equal to 0, then what is the energy? That is, when the dipole is in this direction, then what is the energy of the configuration? And another case is when theta is equal to pi by 2, that is when the dipole is oriented in this direction, in direction of the field, what is the energy? And see which is the minimum energy, and that will give you the answer. That which of these two anti-parallel to each other and perpendicular to the line joining them, or parallel to each other and aligned to the line joining them. The one with the minimum energy is the desired configuration. And I think it will be looks like this one. This one will be the desired configuration, because this one will have a lower energy than this configuration. Just check out yourself. Now we go to the next problem. A point charge is located at the apex of a cone of height h and base radius h. Show that the flux of electric field through the cone due to the point charge is q by 2 pi epsilon naught 1 minus 1 by root 2. That is, this is the figure. So this is my cone. The charge is here. So we have to find out electric flux across the surface of this cone. And one thing you may have seen that the electric field is along the edges, electric field is aligned along the edges. So there is no normal component of the electric field here also. So the flux across these edges will be 0. So whatever the contribution is, this contribution will be from this base. Right? So the total flux to the annular region. So now we will consider this part. Okay. So this is my cone. So this I will consider this some distance. So this is say distance. So the total flux to the annular region is 1 by 4 pi epsilon naught q by a square cos theta. So what is this term? This term is, so if you consider a point here, and this direction is, this angle is theta, then, and this is A, then the electric field here will be 1 by 4 pi epsilon naught q by a square. And what is the component that is perpendicular to this space? That will be cos theta. Right? So that's why q by a square cos theta. And now every point on this circle will give the same contribution. Right? So this is the electric field perpendicular to the face, that is the base, and then we have 2 pi r dr. So this is the area. Flux is electric field into area. So 2 pi r dr is this. So you consider a very annular region of thickness dr. So this is r, this is r, this is a, this is r. So the surface area of the annular region is 2 pi r dr. So this is the total flux to the annular region. What is A? A is equal to h by cos theta. Right? This is my A. This is theta, so it's trivial. So this A will be h by cos theta. And what is R? This is R. R is equal to h tan theta. Now just evaluate. So we have to integrate from theta is equal to 0. Theta is equal to 0. That is, theta is equal to 0 to theta is equal to pi by 4, because this is h and the base radius is 8. So it has to be pi by 4. So do the integration and you should get the answer. Now we go to the next problem. Show that the magnitude of the force experienced by a point charge plus q placed at a distance d from the center of a grounded conducting sphere of radius a less than d is this. So we have to show this is the expression. So what is the problem? Problem is like this. So this is a say grounded conducting sphere. So it is kept at a potential 0. We place a charge here, and because of this charge, this sphere will get, this conducting sphere will get polarized, and it will get polarized, and as a result of that, there will be a force of attraction between this sphere and this charge. So we have to find out what is the force of attraction. So this is a problem. This we will solve using method of image. So what we assume? So the potential here is 0. We want to find out the potential in this region, not inside this region. Inside this region, inside the conducting sphere but outside. So what we will do, we will forget about this conducting sphere and instead we will replace it by a charge here which is placed at a distance d such that the boundary condition is satisfied. That is, the potential at any point on this surface is 0 because of this charge and this charge. If we can if we can find such a charge, then the combination will mimic or simulate whatever the potential will be due to this sphere. You don't have to worry about the sphere anymore. This charge will do the work of this sphere. So that is the method of image, and this happens because of uniqueness theory. So this, if the boundary condition is satisfied, that means whatever solution I get, there will be only one solution satisfying the boundary condition, and that will be the solution. That's it. There won't be a second solution. So if I find a charge like this here, which will satisfy this boundary condition, then we can be rest assured we have found out the solution. So what are we going to do? So we say this is the charge here is alpha and it is placed at a distance d from the center. So what are we going to find out? We will find out alpha and b, unknown. Once we find this, we will know the answer. So what we will say that the potential due to this and this charge will be 0 at this point A, and the potential due to this charge and this charge will be 0 at this point. We don't have to worry about any other points, because if this is guaranteed and this is guaranteed, then this is also guaranteed. That you can check yourself. So this is the potential at A due to the charge Q and charge alpha, right? And this is the potential at B. I have ignored the term 1 by 4 pi epsilon naught here, because eventually it will not be there. And this is the potential at B. And this is 0, this is 0. Remember? So here this is D and this is A. So this distance from P to A is D minus A, and whatever the distance between this charge and this point, that will be your A minus B. And that's how it is seen. Here also you can just convince yourself this is the point B, this is correct. And if you solve, this is not at all difficult to solve for Q and for alpha and B. You will get B is equal to A square by B and alpha is equal to minus QA by B, where A is the radius of the sphere and D is the distance of the test charge that we have put here. That's all. And once you know this charge and this charge, so what is the force between them? And that is the force between this charge and the conductor. And we go to the next problem. So two linear polarizers are placed vertically with the transmission axis of the first polarizer in the vertical orientation and the second polarizer in the horizontal orientation. A half-wave plate placed coaxially between these two cross polarizers is rotating about its axis at an angular frequency omega. At t is equal to 0, the fast axis of the half-wave plate was oriented vertically. A beam of unpolarized light of intensity I0 is incident along the axis of the optical system. Show that the output intensity measured by a detector after the beam passes through the optical system is I0 by 4, 1 minus cos 4 omega t. The problem is like this. So initially we have unpolarized light, and this is my first polarizer. It passes to the first polarizer, and then we have a quarter wave plate, half wave plate, and this is the optic axis. No, sorry. Let's go to this. So this is the first polarizer. Then this is the quarter wave, half wave plate, and this is the optic axis, and this is the second polarizer. So it passes to the first polarizer, then it comes across the optic axis, then it comes across the half wave plate, and then it comes across the second polarizer. So what is the output intensity? So first thing is, if the incident intensity is I0 and the light is unpolarized, then after passing through the first linear polarizer, the intensity becomes I0 by 2. Okay? So what is the logic of this? So if, say, this is the polarizer and this is the, and suppose the light is incident in this direction, then what is the intensity that is passed through the polarizer? This is I0 cos square theta. It is the intensity that is passed through this polarizer. This is the incident direction of the electric field. And now, what is P theta d theta? D theta d theta is the probability that this oscillation will be in a direction between theta and theta plus d theta. That is what it means. So P theta d theta is the probability that this oscillation will be in a direction between theta and theta plus d theta. But here the light is unpolarized. That means there is no preferred direction. So it can be in this direction. With equal probability, it can be in this direction. It can be in this direction. So it's random, completely random. So in that case, what happens? So here I made a mistake. So we indicate from theta is equal to 0 to pi, and this p theta is 0 to p theta is 1 by pi, because this oscillation can be here. So oscillation can be anywhere between in this angle, right? Oscillation can be anywhere between this angle. So p theta, since it is any direction is equally probable, so it will be p theta is equal to 1 by pi, and here I have to put theta is equal to 0 to pi, and then you do this integration. This is very easy to do, and what you will get is half. So this is the average intensity that comes out of the first polarizer. Now, after it comes out from the first polarizer, the light enters the half wave plate. In half wave plate, what happens is half wave plate. This is the half wave plate. So if this is the direction, so the light breaks into extraordinary component and ordinary component. So extraordinary component oscillates along the optic axis, and the ordinary plate, sorry, the ordinary wave, I think, oscillates perpendicular to the optic axis, or it could be the other way around, I have forgot. So that is how it happens, and as a result of that, so what happens is, so one component will be oscillating parallel to this optic axis, and the component will be perpendicular. But the output intensity will remain the same. Nothing will happen to the output intensity. But what happens is that as it goes through the lambda by 2 plate, half wave plate, it picks up so now there are two oscillations. One is along the optic axis, what is perpendicular to optic axis, there will occur a phase difference of pi between them. So they will become, so initially they were in phase, now they will be in opposite phase. So as a result, what happens, if the light was polarized in this direction, and this was, say, theta was the angle between the optic axis and the direction of polarization, the new polarization, direction of polarization, will rotate by twice theta. And so now this is the new direction of polarization, making an angle theta with this optic axis, but with the previous polarizer, it is now making an angle 2 theta. You just convince yourself that if there exists there develops a phase difference of pi between the two components, then if this was the angle between the optic axis and the polarizer before the light entered the half wave plate, after it comes out, this direction will be twist. This direction will be rotated by twice theta. And here theta is, so this optic axis is rotating with some angular velocity omega. So the theta will be here omega t. So this is twice theta will be twice omega t. That's it. If you can understand this, then the direction is with no change in output intensity. So the final intensity will be I0 by 2, and then, so this is the new direction of polarization after coming out from the half wave plate. So this angle is pi by 2 minus 2 theta. That's it. So I0 by 2 was due to the first polarizer, then because of the half wave plate it rotated by twice omega t, and so the new angle between the polarization direction and the second polarizer is now pi by 2 minus 2 omega t. So the amplitude will be I0 by 2 cos square pi by 2 minus 2 omega t. Right? This is pi by 2 minus 2 theta or pi by 2 minus 2 omega t. And from here, try to get this answer. That's very simple. This becomes sine square twice omega t, and I don't have to tell any further. You will be able to do it. We go to the next problem. A conducting spherical soap bubble of radius r with a wall thickness w. So it's a conducting shell, and the thickness of the shell is w, where w is much less than r. That is the radius of the shell, and it is charged to a potential V0. The bubble bursts and takes a spherical shape with potential V0. Now it's not a spherical shell, but it's a solid conducting sphere with potential Vd. Show that this ratio Vd cube W divided by V0 cube R is 1/4. So initially we have the conducting spherical shell in the form of a soap bubble, which was charged to some potential. Then it changes its configuration and becomes a solid sphere, conducting sphere, charged to a potential Vd. And then we have to show this relation is satisfied. So this is a problem of conservation of charge and mass. Rho is the density of the liquid that forms the soap bubble, and r nu is the new radius of the sphere. after it changes its shape. Then if W is much less than R, then I can say that the mass of the shell is 4 pi R square into W, which is the volume of the shell, and multiplied by rho. So that is the mass, and that is equal to 4 pi R cubed by 3. This is the volume of the sphere times 4. This is one relation. Another is 1 by 4 pi epsilon naught q by R is V0, and 1 by 4 pi epsilon naught q by R nu is Vd. Right? So this is the condition that they have also supplied. That this initially it is at potential V0, and after it changes its shape, it is at potential V0. And this is, since it's uniform, since it's charged uniformly, so this is my relation. And from this, arrive at this. It won't be difficult. So these are the 1, 2, 3. From these three relations, to this. And we go to the next problem. A conducting sphere of radius r is placed in a uniform electric field E0 directed along z direction. The electric field potential for outside points is given by V out E0 1 minus r by r whole cubed bracket open bracket closed r cos theta, where r is the distance from the center and theta is the polar angle. Show that the charge density on the surface of the sphere is 3 epsilon naught E0 cos theta. It's not a difficult problem. So V out is, so we have a conducting sphere and the electric field is given for this conducting sphere, and we have to find out the charge density on this surface. Because of electric field, the sphere will be charged, and hence you will have a modified electric field outside. So let's see, it's not difficult. So for a conductor, the normal component of the electric field at the surface is related to its surface charge density divided by epsilon. This we know. So we have to find out the electric field at the surface of the sphere. So what we have to do? We have to do minus grad V. We will do it in spherical polar coordinates. And then we have to find the normal component. So here the normal component is the one corresponding to r cap. So the one corresponding to r cap is En. That's it. Once you have found En, you can find out the sigma, and you have to show this. So do it yourself. There is another problem of point charge. So this is point charge Q is placed at a distance d above an infinite grounded conducting plane. Show that the energy stored in the configuration is this. So this is the distance between the charge and the plane. So we have to show that the potential energy is this. This again not difficult. We have to use the concept of image charge. So we will forget about this. So this is a grounded one. So this is a grounded plane, conducting plane. So if we take a charge, image charge minus q at the same distance, right? And that will ensure that the potential everywhere on this surface is 0. And if that is ensured, whatever the solution we get from this combination will be the correct solution in this region. Not this region, this region. So what is the force between the two charges, the real charge and the image charge? This is the force, Q square 4 pi epsilon naught 2z square. So this is distance z, this is z, so the distance between them is 2z. So this is the force. So what is the energy of the configuration? Maybe the configuration is minus f dz, where I go from z is equal to infinity to z is equal to d. And if you do this, we will get this answer. So completed. Here the trick is, it is tricky in the sense, if the image charge is here, this charge is also here. This charge is not fixed. That's why your answer is different from the usual case. Because this charge, image charge, moves with the real charge. So real charge I am bringing from infinity, then this image charge is also coming from infinity. And as I come closer and closer to the shell, the image charge is also coming closer. And that's how we get this. We get the potential energy of the configuration. So now we go to the last problem of today. 2 point charges 2q and q are placed inside two spherical cavities of equal radii r by 4 in a solid conducting sphere of radius r as shown in the figure. The cavities are placed along the radius at distances r by 2 from the center of the solid sphere. Show that the electric potential at P, which is at a distance of 3r by 2, is 1 by 4 pi epsilon 2 q r. So this is where to find the potential. So this is at a distance of 3r by 2. So here we have two cavities placed at a distance of, so this charge is placed at the center of this cavity and this is placed at this cavity. And this is as a radius of r by 4. So what is the potential? So potential is, if you place a charge 2q here, inside you will have a minus 2q charge. And here if you place a q charge, inside you will have a minus q charge. Right? So this and this induced charge, this and this induced charge will ensure that the electric field inside this conductor is 0. And now we have extra 3q charge, so that will be spread uniformly on this sphere. And because this charge is uniformly spread on this sphere, because of this charge configuration outside on this surface, the electric field will be 0 because of this. So this charge and the induced charge, this charge and the induced charge here on the inside ensure that the electric field is 0. And then the extra charge gets uniformly smeared on the surface. So we have 3Q. So that's it. The E field is 0 inside because of the internal arrangement of the charges on the inside surface of the conductor. The induced charge on the outside is uniform and 3Q. That's it. And now use Gauss's theorem to find the potential outside. And you will get the answer. And we'll stop here today and we'll soon meet again with the second part of this series on electromagnetism. Thank you.